So we can start this last session of school plus workshop, everything. And so it's my pleasure to introduce you to Alessandro Rudi, which will do his finishing lecture on Ph.D. models for non-negative functions. Please.
Thanks, Simone. Okay, so let's finish the story we started a few days ago. So now we have an ideal problem that we want to solve. I'm just recalling the things from the other days. Okay, so this is the problem. A is a positive operators over H. And so we know that this problem is a solution because we assume that H of X minus C star, where C star is equal to the minimum of H, okay, can be written as so what are we saying here is that the function H, this H, let's say, minus C star is non-negative and admits a decomposition, and so an operator A star, okay? So in particular, you have a sufficient condition for this is that, as we have seen yesterday, the function H is an isolated global minimum, okay? So in that case, you can do the construction and build explicitly. So H, so let's say, why d over 2 plus 2? Because d over plus 2, because we saw that we obtain a construction. We can, with the theorem we have seen yesterday, we write H as a sum of squares of functions that are Cm minus 2. And the d over 2 is because we want that the functions Cm are in the Sobolev space. So using the theorem of yesterday, we can decompose H as the sum of, let's say, Vj square okay, and Vj are in Cm minus 2, okay, and since m minus 2 is larger than d over 2, then this can be embedded in a Sobolev space, okay? And so this means that if we choose phi to be the feature map, the map, so if you want H phi is the RKHS associated to Wm minus 2, okay? And so what does it mean? It means that you choose the so we are doing everything on to avoid the boundary condition 0, 1 to the d and h and periodic, okay? Periodic, okay? Otherwise, we should study what happens on the boundary, but we keep it simple today. Okay, and so if you can see at this level, let's do like this. Okay, let's write it explicitly. So let's build an RKHS that is equivalent to W n minus 2 periodic. We can choose, for example, Kx prime x equal to okay. So with this kernel, you have an RKHS that is equivalent, whose norm, H norm, is equivalent to the norm of W n minus 2 periodic. Okay. So H under those conditions on this one, and the fact that in the minimum the Hessian is strictly positive, admits this decomposition, the function V live in the space H. And so we can write H of X now as Vj. And now we can apply the reproducing property. And this become okay. And this is your operator A star. Okay, so this problem admits a solution that is, this problem has a solution because there is at least one admissible point here that is A star and G star. Because if you plug A star here and G star, C star, this one becomes 0 everywhere. Okay. In particular, if you want the A star I put here is not the one with minimum norm, the solution of this problem will be C star, because in any case, you need an operator A that satisfies this formula everywhere for any X. So you will take another operator that is equivalent to H of X minus C star, but where you are penalizing the norm. So you will take among all the class of operators satisfying this, the Ph.D. operator with minimum norm. Okay. What we proved here is that there exists at least one. Okay. So let's call now the solution C star A bar. Okay. What we know by construction is that the trace of A bar is bounded by trace of A star. Okay. But we know that in practice we don't know how to solve this problem. We discretize. So the problem we really solve with our computer is this one. Yes, you're not there. Okay, you changed place.
But the regularizer you have chosen lambda 3 enforces the problem.
Sorry.
The regularizer you choose in lambda 3
Yes,
enforce the problem to choose the solution A bar with minimum norm, or it is something that we need to do a posteriori? It is another.
No, well, among all the operators, so here I showed. So if H has the two properties, so it has these regularity properties and has a global minimum, isolated global minimum with strictly positive Hessian, then with the construction we did yesterday, you prove that it can be written like this. The function Vj belong to the RKHS, and so you can build explicitly one operator, okay, that we call a star, such that h of x minus c star is equal to this formula for any x, okay? So there exists one a star that is equal to this, but it's not unique in general, okay? And so this problem among all the operators that satisfy the equality for any x will take the one with minimum trace, because we are penalizing the trace. So C star, it's fixed. The only thing you can improve is the trace of A. So among all of them, it will take the smallest one. The set is bounded from below because since it is a set of positive operators, the trace is bounded from below by 0. So there exists one. Good. Yes.
What if you can make the C a little bit larger, but make the trace of A much smaller?
But you cannot, because you have to satisfy this inequality. So you cannot take C. If you take C larger, you are putting a region of the space to be negative. And so
sorry,
no,
I meant the opposite. What if I make C smaller?
Yeah, so we will discuss this. Okay, so no, you're right. So indeed, so this one can be in general, depending on lambda, can be smaller. But indeed, so you're right. So you obtain the solution with lambda tending to 0. And so in the limit with lambda tending to 0, you obtain the A bar. Okay. But we are going to see that the error you are going to pay is in the order of lambda trace of A star. So the error is bounded by lambda. This is true. So, okay. So let's call C bar, A bar, what you obtain here. Okay. And so now we have three set of objects: C hat, A hat, C bar, A bar, and C star, A star. This is what we would like. So we don't care about A because it's just a construction we did to find C, but what we would like to fix this is what we compute. This is a theoretical object. And this is what we would like to obtain. So we are going to study in the end the distance between C star and C hat. Okay. Yes.
Alessandro,
Yes.
can I ask another question?
Yes.
We want to choose a solution with minimal norm for A for computational reason, or there are also other kind of reason.
Well, but in any case, I mean, here you have a class of operators that give you the same object. So you want to choose one, okay? You could choose the one with maximum norm, but then you have to, so all the construction pays the norm of it. So let's choose the one with minimum norm. And this is what you do in learning in general, or in approximation, because the regularity of your object depends on the norm, kind of one of the norm you choose for the approximation you are trying to do, no? So, okay. So you see that this problem here is exactly the same, but we restricted the set of inequalities, okay? So we choose a set of inequalities that is just over the points, let's say, for any I equal 1 to n. And here is for any x in 0, 1 to the d. And the assumption is that you choose the points x1 to xn in the set. Okay? So This one is the same functional, but a set of constraints. So that is smaller. And so the problem above is more constrained. And so the associated minimum will be larger than the minimum you can achieve here. So what you have is that C hat plus lambda trace of A hat is smaller than C bar plus lambda trace of A bar. Okay, but you know something more. So C bar, A bar is the solution of the problem, but C star, A star is an admissible solution of the problem above. So you have, sorry, the minus. Okay. So this is the first inequality. Now we are going to obtain another inequality that puts C hat and C star in the other direction. So we can bound it from below and from the above. So we keep this one. So is it clear? So this one is smaller because it's a more relaxed problem with respect to this one. And this one is smaller than this one because this is the optimum of the functional, and this is just the value you obtain with an admissible solution. Okay, so now let's try to derive some equality in the opposite direction. And this is where we need approximation property. So the question is how this reduced set of equalities approximates the dense set. Okay. So, and here we just start from, so this the one I'm showing is an interpolation result that you can apply wherever you want. In particular, so I present this for any set of equalities, then we see what happens if you use it with Ph.D. models. So this theorem allows you to derive, if you want, a kind of interpolation results for a set of inequalities. And you do this adding Ph.D. models. So let's start with this result. So you have a function, okay, that is in some Hilbert space H. And your function satisfies u of x I equals 0 for any I equal 1 to n, okay? The question now I pose to you, can I have a bound on u L infinity? Okay, over a set omega. So let's say that okay. So given this and the fact that the u is in H, can I have a bound on L infinity? So let's massage now this L infinity norm. Okay, how would you write it? This is the sup of x in omega of ux. But now this one is in H, so you can apply the well, you can rewrite in terms of the representer property, no? So it will be sup of x in omega of okay. But now let's consider something, okay? So you remember the operator U, P, the projection operator we defined yesterday. Okay, so let's take P, the projection operator, over the span of the feature maps applied to x1, xn. So let's take P such that the range of P is equal to the span of px1, xn and P is a projection operator, okay? Okay, we did yesterday an explicit construction for this P. So the assumption is that the points are all distinct, and as we did, yes.
For the equality, the sub U and the sub phi dot U, how do you have the equality here? Between the two.
Yes, this one is a continuous function.
Yeah. And then how do you have equality between this? And then
well, dell'infinity.
Oh, sorry, going the other way.
Yeah, so I want.
So you have equality between the supremum over U and the supremum of
this one.
Yes.
Well, U is a function in H. H is a RHS.
Okay.
The fundamental property of RHS is that any function in H, the evaluation of any function in H is equal to the inner product of U with the map.
Okay.
So this is the fundamental property of RHS.
Okay. Okay.
And this is why so it's a way to if you want, so we can write the Dirac delta explicitly and use it. Okay. So this is why we like RHS.
Okay. Thank you.
And then you can do this, you can write derivatives, whatever, in terms of your linear operation, not applied to the function, but to the other object, to the evaluation functional.
Okay. Brilliant.
Okay, and this is what you are going to do here too. So this is your function, this is your projection operator. Yesterday we wrote it explicitly as S star G minus 1S, okay? But now let's do P of U. What is P of U? It will be S star G minus 1 S of U. Let's compute S of U. S of U is equal to phi of x1 U phi of x n U. Okay? But by assumption, so phi of x U is just the evaluation, and so we are just evaluating U in the points xi, but this is 0. So this is just a vector 0. And so S star G minus 1 vector 0 is just 0. So because what it is the the interpolator with smallest norm, the interpolator of U, as we said yesterday, with smallest norm in H. So it's a function that interpolates U in all the points, but U is 0 in all the points, and the smallest interpolator is 0. And we proved here. So this is equivalent to supremum x in omega of phi of x U minus PU. And we can do this since this is the 0 vector. Okay? And so this is the supremum of x in omega of, now you can gather U and U here, so it will be I minus PU. So you can write this as I minus P phi of x U. Okay. Now you can do Cauchy-Schwarz, and so this is smaller than the norm in H of U times this epsilon that depends on how you distribute the points where your function U is 0, and on the specific properties of your RHS. And so this one is supremum of x in omega of I minus P phi of x. But now you see, it just depends on properties of your points that are encoded here in P, and the RHS you choose, that is your phi. And clearly the norm you put here. For example, later, for the kernel we wrote, we are going to compute, to bound this quantity. So to give epsilon a specific value depending on how many points do we take on the grid. Okay. So for now, let's use this. And then later we are going to, hopefully, if we have time to bound this quantity. But otherwise, this is the classical, since we are doing everything on the periodic functions on Sobolev, it's a classical result. So if we cannot prove it, I can send you to books where it is proven. Okay, so we have this. Now let's try to use this result. Okay. So now let's define U as H minus C minus F of A. Okay. So does F of A belong to the space? This is the question, because the assumption is that U belongs to H. So if it is written like this, what is F of A? F of A is okay. So we want this, if you want, written like this, to belong to H. And to have this, we need to require the property that we introduced yesterday, that is F of times G. Okay, this holds for Sobolev spaces. We can also prove it. You can prove in general for translation invariant kernels that are regular enough. In particular, it holds for Sobolev space with smoothness larger than d over 2. Okay, indeed they are Banach algebras. So why, if we have this property, this holds? Well, because this one is written like so A is a trace class, because we are regularizing over the trace. And so this corresponds, so if you take now the decomposition of A, okay, the sequence on lambda is summable. So you have this lambda j Vj square. Okay. And so by this property, if you do the norm of F of A in H, this is bounded by Q but if you see, this is exactly Q trace of A. Okay. And then the same thing. If you want to prove it step by step, you take the limit, you do you approximate your series, and then you show that it converges somewhere, and this somewhere is exactly F of A. So. Okay, so now we have that U is in H. Okay, we can also bound the norm of U in H, that is the norm of H plus C. Okay, plus, so this one we already did it, and is Q trace of A. Okay, you need the function 1 to be in the space in this particular case. So, okay, so at this point, so we require that as we do in the approximated problem, Uxi is equal to 0 for any I from 1 to n. Okay, this is what we require in the problem that we compute. That is what? This is h of xi minus c minus f of a xi equal to 0, okay? And the question is, now, if we require this on this discrete set of points, which is the error we incur on the rest of the space, okay? And we are going to use the result, this result here, okay? So we have, so this requirement for any I from 1 to n implies that so if you want the supremum of x in our space 0, 1 to the d is smaller than the norm of u epsilon, okay? Why do we care about this? Well, because this in particular implies that this holds also in the point of the global optimum, okay? Here you have this everywhere, this inequality. So in particular in the point x star, such that corresponds hx star equal to c star. So it is the global optimum, okay? And so this implies that h of x star that is equal to c star minus c minus f of a x star smaller than UH epsilon, okay? And which side do we care of this absolute value? We care about the other side. So in particular, we write that f of a of x star plus c minus h of x star is smaller than UH epsilon, okay? Now you have this term. What do you do with this term? Well, this term is always non-negative because it is a Ph.D. model, and this is why we wanted a Ph.D. model here. So you can bound this as C minus HX star, that is C star. So C minus C star is bounded by the norm of UH epsilon. Okay? So I removed it. Okay. So with this, and this also in general, if you have a set of inequalities, okay, a dense set of inequalities, you transform it in a dense set of equalities, adding Ph.D. models, then you subsample your set of equalities, and you can use the same result. You will have, at the end, you will have that your inequalities will hold up to error epsilon in the whole region. Okay, and what you gain is that you gain the fast rates induced by interpolation theory. Okay, so from the previous reasoning, we obtained that C hat plus lambda trace of A hat is smaller than C star minus C star plus lambda trace of A star. Okay? From this reasoning, instead, you obtain that this holds for any C and H and A that satisfy the constraint, so in particular for C hat and A hat. So you obtain that C hat minus C star is bounded by UH epsilon. Okay, so now the idea is let's use those two. Okay, so in particular, you bring now C on the other side. And so what you are saying is that, so from this one, you derive that C star minus C hat is bounded by lambda trace of A star. And you should bring on the other side this one, but since the trace of A star, A hat is a Ph.D. is a positive operator, so the trace is always non-negative. So if you bring on the other side, well, let's do it. It's easier to write. So this is bounded by lambda trace of A star. So you put the two things together and you have a bound over the error you achieve. So you have C hat minus C star bounded by U H epsilon bounded by minus lambda trace of A star. Okay, so we could stop the proof here. Actually, it's not finished. We have some details. So because U, the norm of U, as you have seen, well, it was written here. It's the bound of this depends on epsilon. So here you have epsilon times there was also the absolute value of C and the absolute and the trace of A hat. Okay, the norm of U itself was okay, so now this you can do as an exercise. So you gain this. Now you have to prove that if you take lambda large enough, in particular something like larger than Q epsilon over 1 minus epsilon, if you choose this lambda, actually you can just express the bound only in terms of trace of A star, the norm of H, and the norm of 1H. You want lambda small here. Here you would like to have lambda 0, okay? But then you see that you see from here actually that in a sense the trace of A hat is bounded by something depending on the trace of A star minus the difference of the two. So if you take lambda 0, you are enhancing too much. So if you write it, no, now you can write it, the trace of A hat smaller than C hat minus C star over lambda plus trace of A star. Okay, so now you would like to choose a lambda such that this quantity is bounded by two times trace of A star. Okay, so you cannot take lambda too big, too small. Sorry, and so you prove that there is a condition that satisfies this, something like this. Okay, so lambda in the order of epsilon. Okay. We can do it if you want. It's just that it's boring. It's just playing with we have two inequalities until we obtain the result. Yes.
Once you have, finished your optimization process, how do you find the value of X in which that corresponds to the minimum?
The proof I did here is just to find the value of the global minimum, not the minimizer here.
Okay.
In this construction. But you can extend the same identical construction for another problem. So the problem that you are doing here is I have my function. I want to find the highest hyperplane that is always below the function.
Exactly.
And so it will touch the function when C is the global minimum. But you can do something else. So you have a function, and instead of asking this, you can ask which is the highest, the parabola whose center is highest, and always below the function, okay? And if you take the parabola, let's say with the small curvature, so if the curvature is small enough, because of course, if this is your function, you take this parabola, it can never be below, okay? But if you take it large enough, since you are on a bounded set, you see that if you push this on top, it will translate until it will arrive here.
Yeah.
Okay. And so you just impose this problem. This problem again is convex, and because you keep fixed the curvature of the parabola. Okay. And that's it. And so in this way, you will find the global minimizer. So not only the global minimum, also the global minimizer. Of course, for this specific construction, you need one global minimum, because if you have these, well, let's say that they are on the same level, okay? There is no parabola with non-zero curvature, no, that can do this. Yes.
Can you show the other blackboard, please?
Yes.
Okay. The last inequality on the bottom right is that kind of inequality already give us a bilateral inequality on C hat minus C star. So, because we have abandoned.
Yes, but this is the fact is that this is so you did this not because you wanted some equality. The original problem that you were solving was minimum of minus C h of x minus C larger or equal than 0. Okay. In the other direction, the inequality is not interesting because this can be arbitrarily large. F of A of x star is a non-negative value. And on this side, we bounded it because it is strictly non-negative. And so you can eliminate it and you go to the quantity you are interested in. On the other side, well, I finish this. On the other side, you have C star minus C minus F of A smaller than UH epsilon. You bring this on the other side, and you are saying this one is bounded by epsilon plus a quantity that can be arbitrarily large. So it's not interesting. But the problem is constructed such that the other side is bounded by the construction of the problem, and the fact that you add the non-negative, the Ph.D. model gives you exactly the inequality in the direction you are interested in. Okay, what is this? If you want in X star, this is C star minus C larger than 0. Okay. Exactly. So we are saying that C minus C star is smaller than epsilon. So what you are obtaining here is C star minus C is larger than UH epsilon. That is what we were interested in, minus, sorry.
So that means that when we are minimizing that problem, we are not going to below the
Exactly, you
minimum.
are not going to below. You are going below at most this one, this quantity. Okay. So we have half hour. If you want, we can prove this. So I told you that this epsilon is very small because of interpolation properties of the space. Maybe we want to see one example. Yes, please.
Question is, so I guess you can handle the boundary case in general.
Yes, yes.
So in that case, like, in order to actually find the minimizer, could you just do like a search procedure? So you start off with your domain, which is like a cube, and then you just cut it in half, and then on each half check if the value is of the minimum, and then
absolutely. This is especially if it is just one. If there are some assume that there is one global minimum, you can divide it in two. But
if I just care about finding any global minimum, it doesn't really matter, right? So what I'm saying is, like, let's say I know C star.
Yes.
Then I cut the domain in half. I check if the minimum of the function is
C star. You have to solve this problem once and find C star. No, then you can.
Yeah. But
yes, then you can cut the space. So you solve the problem on the whole space once.
Yeah, to find C star,
and then you can use indeed a. Yeah, I mean this could be possible, I guess, to do a divide procedure, no, where you cut the space in two and you solve the problem on one slice and the other. The one that brings as C star, that achieves C star, is the good one, and you continue to cut there.
Yeah, exactly.
No, definitely. So if you want, we can see this one. This kind of result exists. So they are very well studied in interpolation theory. And in general, so I can give you the general result is something like this. It's the one from Wendland. There is a very nice book of Wendland. It tells you that if you have a function u that is in WMP, so even for other Sobolev spaces, okay? And you have u of xi equal to 0. And x1, xn are in omega, the set omega you're interested in, okay? And then you have a kind of covering properties, and then there exists tau, that is the Hausdorff distance between omega and x. So x is your set of points. Okay. So what does it mean if you want? So this is your omega, this is your set of points. It is a subset. Okay. So if you want, it is, so this one is the farthest, the point in omega that is farthest from one point in x star. So you can write it as the sup of x in omega of min okay, and the result works like this. So the L infinity in omega is bounded by some constant that depends only on M, P, and D of U, W, and P, and tau 2 minus M plus D over P. Okay? So this is the kind of result. And you see, this takes into account also how well the points are distributed. Okay? And so in the grid, if you have the points well distributed that cover the whole space, or let's say the grid, then you can express tau with respect to n and see. So you see the good thing is that the rate goes to 0 with respect to this distance with the power m, that is the smoothness. Okay. This is to take into account the fact that the derivatives are not in general L-infinity, they could diverge. So in particular, if you want to consider C function that m times differentiable, you could embed it in W infinity and minus 1. So, okay, so now we are going to prove a result like this, but so here it is very general. You can take the points wherever you want and so on. We do it for Sobole, so functions that are Wm2 over the torus, okay, and where the points are on the grid. So because there we can just use Fourier to do this. Okay, so to prove at least one case where we can do it by hand. Okay, that's clear. So let's see first to have an order of magnitude. If the points are on a grid and we are in a cube, which would be the value of tau, okay? So let's take this example to understand. Let's say that this is 0,1 to the d, x1, xn on a grid, okay? So if we are in this setting, tau will be in the order of n minus 1 over d, okay? And so the rate that you would obtain would be something like, for any function u in the space, I don't know why I wrote this. For any function u, so no, sorry. Indeed. It's tau to power m, because tau is arbitrarily small. You can choose it very small, and it's, I mean, you gain an m power. So if it is Lipschitz, it's 1. There will be the function will be bounded by 1, and this is trivial to prove. And the good thing of this result is that you can achieve larger m. Okay, so. And then here you obtain instead the result with the minus, and it will be this. So this is how the error decays with the number of points if the points are well distributed in the space. Let's say they are recovering. Okay. So you see that if m is regular enough, this one, so you can achieve an interpolation that avoids the curse of dimensionality, at least in the rate, then you still pay here the constant depends on d in particular, and it depends in typical. We will obtain a result where we will have 2 to the d, for example, and in general this is not avoidable. Okay, so is that clear? So we are in a setting where h, yes.
Can I ask a question on the course?
Yes.
Yeah. But could we say that the course of dimensionality stands by the fact that to visit an hypercube we need that kind of of number of an exponential number of points. So to know U in a sufficiently large set of points to bound the infinity norm.
Yes, but the question here is that you want there, so you want to make this arbitrarily small. So the question is, if I want to double the precision, how many points I should take more, no? And if M is large enough, let's say if M is, so you can make this a constant. Let's say that you make it 1, okay? And so you are saying if I want to double the precision, I have to take a double the point. I don't have to take 2 to the D times the point I had previously, okay? Then to arrive to precision 1, you have to pay this constant, okay? And so there you have to explore the
They're
space.
different. They're different kind of costs.
Well, let's say that this is 2 to the D and minus 1, okay? So I say, okay, let's arrive to error 1. Okay, first you need to take 2 to the D points. Okay, and then if you want to obtain error 1/2, you have to double the points you take before. Okay, you don't have to take another 2 to the D factor. Okay.
So I have a question, which is like the assumption that we started with on the function that we're trying to minimize.
Yes.
Essentially, it's like a Sobolev assumption with p equals infinity.
Yes.
But then like we passed to the RKHS, and then now we're applying this approximation result for p equals 2.
Yes.
So maybe we did the order of the arguments wrong. Maybe we should have been applying the approximation result to the function before we passed to the RKHS in order to take advantage of the better approximation properties.
Indeed, it is what we do in the paper. We do exactly like this.
Okay.
But the fact is that now we can prove the result explicitly. So I want you to use it just once instead of using the result for let's say WM infinity for the constraint, and then the other result later for the Hilbert space. So that's because indeed. So what Sinho is saying is that you can consider your function embedded in a larger space, okay? So which is so our, but you see, so because your function, so by construction our f of a, so let's say that h is Wm infinity, okay? But in any case, f of a is W something 2, okay? And this something must be at least in the order of h, but actually smaller. Because we are doing a construction that passes through an RKHS. So in any case, we have to consider all possible functions. So we need the result where we can take into account the fact that our function, so h is not RKHS, maybe not, it's just maybe CM, but f of a, it is in h. You see what I'm saying? So we are going to consider then a function that is h minus c minus f of a. So this one can be CM, okay? But this one, in any case, will be in h. So
I was wondering though, like if you can do all the approximation theory at the level of CM and never have to do an approximation for
but the fact is that WM2 yes, so so you want to work in a larger space, let's say C, but this one is M minus D over 2. Okay, so in any case, you are going to pay this factor. So this one, let's say this one is WM2. You want to use a result with the P equal infinity. So you need to do. Okay. Because this one has derivatives that may go to infinity. They are just L2. While this one has all the derivatives that are bounded. So
I guess I was wondering, like, if you start off with your function h, which belongs to CM, and then you argue that the problem of minimizing h can be reduced to like a finite set of inequalities up to error epsilon, and this finite set of inequalities is determined by the approximation in CM. And then at that point, you already have a finite dimensional problem, and then you just pass it to like a finite dimensional SDP.
It is exactly what we do, but then we need an inequality that can be applied everywhere. And to have this inequality, so how do you resort? So you would like to have a bound of this form, L infinity of your space omega, okay? So somewhere you have to do this, okay? Where one function is in H, because you want to bound.
But I'm not even in H anymore. I'm just in the span of phi of xi.
Yes, but how can you bound the norm of this object? You can bound if you say this norm will tend to the norm of something. It must be finite, no? And so a way to do this is to say that there exists an A star, okay, where this object will tend. So we can have a look to this, but I don't think there is an easy answer.
Yeah, I guess so. I think I understand what Sinho is saying, because you basically use an inequality, right? Which is the kind, okay, I want to bound what is FA. What you need is really just FA in ECM.
Yes.
In the end.
Yes.
And you say, okay, but FA is in my RKHS, so I bound it by the norm in H, which you know it's basically more or less the trace of A, plus, and then you pass to the CM by using this inequality. But if you know already that your FA is a finite combination of some phi I.
No, yes, but I cannot do F of A CM. This in general is not finite. What is finite is CM minus D over 2.
Yes, but for example, if you take,
So either I get rid of the Hilbert space structure, and so I approximate function as CM.
I think this is what you were saying, right?
So if you see in all the construction, we use the representer prop. So to show that there exists a finite dimensional construction, we used so the fact that you can compute it in practice. No, we showed that A hat now can be written as Bij. So if you want that F of AX can be written in a finite form as KX xi, KX xj, okay, where K is the kernel. So to have this result, you need an RKHS. If you just take a function in CM, I don't know if I don't.
So this is fine.
I know exactly, but to obtain a finite computability,
this is fine. So what I want to say, and I guess I don't know if it is what Sinho wanted to say, but I think it's on the same line. You solve the problem in the RKHS, and maybe then a posteriori you show that your inequality there is better than what you obtain by estimating with the RKHS norm. Because maybe KX,
we could have a look to this.
because maybe this KX xi, KX xj, in the way your points are put, that function there, KX xi, KX xj, it's better behaved than the.
So if you put here A star, I would say yes, because A star, F of A star is equal pointwise to H minus C. But this inequality holds for any C and any A. In particular for C hat, A hat, for C bar, A bar, no? So, and there you are minimizing the trace norm that is in Hilbert. So you are taking the function with the smallest Hilbert norm. So the question is, doing this,
you define A star, A hat via RKHS, but then when you do the estimates, you can also forget about where they came from, because then maybe it's better behaved, right? So let me give an example. Like when you do integral of, I don't know, you're minimizing the Dirichlet integral, and when you're minimizing the Dirichlet integral, you have to take it in W12. But then when you estimate the I don't know, the W22 norm, it's better than infinity. So you don't just use the embedding that you already have, but it's
Let's have a
actually
look.
better because maybe the solution have some properties more, or because
exactly.
you chose the points xi xj in a way that
So the
you
solution,
can estimate better.
the
right?
solution without regularization, that will be a star, and so the function you built it in H, but it will be just equal to this, okay? Because here you will have 0, no? So it will be CM. But I don't know if by regularizing, because we are regularizing with something that depends on the norm H. So either we regularize with something that depends only on the CM norm, but I wouldn't know how to do it in a reasonable way. Yeah, so if we regularize with a norm that depends on the CM norm, then yes, the result will be with the finite CM norm. So that, yeah, okay. Okay, that's it. Yeah, yes, yeah. We wanted to prove the. Okay, so now we have only 9 minutes, so let's see what we can do. Yeah, so we want to study this, okay? Let's say, let's take an X, we want to study this quantity, okay? So P is the projection operator. So now we just, this all, what we are doing here now holds for any Hilbert space, then we will specify a bit more the result. So P, when you apply P to a function, you are taking the minimum norm solution. So you are trying to do this. So this will be equal to the minimum, we want to the infimum, of V equal to okay, so you are projecting over the space, over the range of your the feature maps applied to the points, and so you want to represent now phi of x with a linear combination of phi's over the points, and so you are minimizing something like this, okay? Okay, so now what we are doing is that in general, we don't want to, in our case, we will not solve this problem. We will just take a sequence that we like. So this is bounded by phi of x minus one specific sequence that now we are going to build of phi of xq. Okay. So so now we take our kernel. So in general, so we took the kernel x. Okay, and so so where UL is and you know also that phi of x prime phi of x must be equal to your kernel, okay? So in particular, what you have is that UL UM is equal to KL delta LM. Okay. Just use the definition of the inner product with respect to the Fourier transform that we had before. So actually now we can just expand this as okay, so the function UL are all orthogonal, one to the other. So this is just the sum over L in ZD of, yeah, so indeed, sorry, this is, the kernel gives you this. Indeed, if you have two functions, beta L UL gamma M UM, the result will be the sum of beta L gamma M. Okay, this is the inner product for the space that we defined in the first place. And so you will have something like, yes. Okay, so now the trick is to choose, so first to select the points on the grid, and then to choose some coefficients for alpha q that will minimize, will allow us to control this sum. Okay. And here we can just use, I don't know if you did, you played a bit with DFT matrices in your life, but we are just doing this. We are using a very simple inequality. The fact that if you have E2I, let's say L minus M S, okay, with S from 0 okay, so this one, so let's assume now, so L minus M is in N, and okay, so in this case, it is just a geometric sum if you want. So you can write it as 1 minus E2I pi L minus M to Q plus 1. So what we are doing here is that we are summing up to power 2Q. So here we would put 2Q plus 1 divided by 1 minus E 2 pi E. Okay, you see that this one, gives you an integer, and so this will be 1. So this is 0. Instead, if L is equal to M, or more generally, if L minus M is of this form, is equal to 2q plus 1 times, well, is a multiple of 2q plus 1, you have that this 1 will be 1, and so you will have okay? And so this tells us how to choose now the alpha q, okay? And so first it tells you that you want to normalize by 2q plus 1, and then it tells you that you can just do a linear combination of your UL over the points up to so multiplied by the associated Fourier. What time is it? So well, let's do in 1D, and then I mean you can do multiple D. Okay, so since it's just 2 minutes after 10. So here you can build a matrix. Okay, let's call it no, okay. So let's do it. So the idea here now is that so we select the point on a grid. Okay, so we take Q. So our point xq is just Q plus constant Q divided to Q plus 1, where Q is in okay, so we select so this one is so those are points that go from 0 to Q in all component. So this one is a vector of integers that is d-dimensional. It contains number between integers between minus q and q, and so this one is mapped between 0 and 2q divided to q plus 1. Okay, so if we do this now, we have that. So we would like to find now some alpha at q that multiplied by this and using this property will give you a value that is equal to ulx. Okay, so now you have so now we want to set our alpha at q equal to, take the same set, okay, and then we need the normalization factor to take into account this. That should be exactly 1 over 2q plus 1. Okay, to the d. Okay, so now let's see what happens if we plug this alpha at q here. Let's see what we obtain. and we are going to use this formula. Of course, this is in 1D. You can imagine that now you can multiply by all the so you can just do it multiple D and you will obtain the same result. That is well, that you have 0 unless L minus M is a vector where all the components are a multiple of 2Q plus 1, okay? And so, let's see what happens. So we are doing alpha hat Q ULX Q. Okay, now I expand this. And then I have this one. Okay, what is this? Well, this one is exactly E 2 pi I how did I put the sign? So it is L minus M over 2 plus Q transpose Q. Okay? So, okay. So let's see what happens. And luckily we are there. So now you can just bring the summation over M outside, and so it is okay. So now, yeah, I forgot this plus Q here. Indeed. So now we do a shift. So instead of going from Q from minus Q to Q, since we are just adding Q, we shift it from zeros to Q. So but this is exactly the multidimensional version of the formula you have seen before. So this one, it gives you 0 if L minus M can be written as 2Q, so cannot be written as 2Q plus 1 times an integer, okay? So in particular, what we have, so let's write it like this. So we forgot the 1 over 2q plus 1 to the d. This normalizing constant is exactly the one you take here. So this one would be 2q plus 1 to the d, and then a delta of, if you want, say, modulus 2q plus 1 component wise, okay? Okay, so that's it. At this point, we just plug it inside and we obtain okay, so now we can divide the sum. So this is the solution we had. What is this? This is just sum of alpha q hat ul xq. Okay, so now we can plug in the formula, in this formula here. And so what you have is KL ul of x minus I know that it is super boring. And it's more boring for me because I did also yesterday night. So it's the second time I'm doing it. So now you can divide this in two parts. So the one where L is in the same range, and so this one will be 0, and the rest, okay? So now you can divide it in, if you want. Let's call all of these CL, okay? Now 1 second, so we'll be fast. CL. Okay, so now here, if you take L between minus Q and Q, you will always have an M that makes it equal to 0. So this one will be UL X, okay? M will be selected as equal to L. And so this term, so this one cancels and this term disappears. So we are left with this term. This one, if you see, in any case, will be one, you don't know, so it will be one component that corresponds to L modulus to Q plus 1. Okay, you don't know which one, but in any case will be UM of X for, so UM L of X. But in any case, those are Fourier components, so they are bounded between -1 and 1 in modulus. So this one is bounded by, this is bounded by 1, this is bounded by 1, this is bounded at most by 2, and so to the square, so it is just 4 times sum K of L with L Z to the D in the okay, so now to finish this proof, we have just to find a bound for this sum. And so we choose KL to be 1 over 1 plus the L2 norm to the square of M. So for simplicity, we bound this with L infinity norm. Okay, because what we are doing here is that we have our space, our lattice. We are just removing a cube. Okay, and so the L infinity norm is the right norm to analyze this. And so we bound this with L infinity to M. Okay, and in particular, at this point, we bound it even more like L infinity minus 2M. Okay, and so now we have. So one way to express this sum is to do this sum, slicing it with shells that are of Del infinity, shells of Del infinity balls. Okay, and so we write this sum K of L as let's say T from Q plus 1 to infinity of L infinity equal to T. Okay, and we divided, so just we sliced the same space of K of L. But you see already that now K of L depends only on Del infinity norm, so only on T. So this is for time T equal Q plus 1 to infinity of T minus QM of okay, so now we have to estimate that you have to compute how many points we have in the shell, and this is what? So we take the cube, the external cube minus the internal cube. So this one is equal to T plus 1 to the D minus 2T minus 1 to the D. Okay. And this one, we can write it as yeah. So the difference between the two, so 2 times okay, so, and this is bounded by 2 times okay. The important thing is that why I did it so in detail, because I wanted to obtain D minus 1, so to gain this minus 1. That is just the volume of the surface of the thing. Okay, so this one is now so, and now we can bound this as yeah, we can put let's bring 2 to the outside. Okay, so So we have what here? So let's say we have d plus 1. Let's do this. We can do it correctly. Well, you see where we are going now. I will write it as t minus 2m plus 1, no, minus 1 plus d, and then we will do the sum. Okay. So we write it as t minus 2m. Right, yes. And at this point, we can do this plus t minus 1. Okay, so this one is bounded by 1 plus 1 to q d minus 1. And for simplicity, if you want, we can bound it with another 2d minus 1. We want to be sloppy, to be fast. And so for 2d minus 2, at this point, you bound it with the integral. So this is bounded by 4, since it is monotone decreasing, 2d minus 2 from q to infinity. And this one is the bound now on the norm. So if you go back here, we can bound this with so and this also, you see, you have the naturally, so to compute the integral, you need them to be strictly larger than d over 2. So you obtain it. Okay, so now let's write it in terms of n. So we have, so n is equal to 2q plus 1 to power d, okay? So if you agree with me, we can get rid of the plus 1 and just to have the rate. So it is n 1 over d. So we will have 1/2 n1 over d is equal to q. And so it's what we are going to plug inside. And so this is, if you want now, 2d, 2 to the 2d. Yeah, so n alla meno minus 1 over d. And that's it. Okay, so now if you take this, so this was epsilon square, right? Now let's take the square root. We have that epsilon is bounded by it is exactly the rate that we have seen in the general case before. And so now you plug it in the algorithm and you will obtain the convergence rate of the algorithm to the optima, to the global minimum. And that's it. So thanks for this additional half hour.
So thank you very much. So let us begin with the last lecture of the workshop, last lecture of the school workshop, and also last lecture of Sinho, which will conclude his course on sampling of long-concave measures. So please, Sinho.
Okay. Yeah, thanks everyone for being here on this last day. Yeah, so today I want to discuss some stuff about like kind of revisiting this view of sampling as optimization. But a quick recap first of all of what we talked about last time. And then I'll also like recap like the brief discussion we had at the last like 10 minutes or so. Okay, so we saw that the sampling problem on the space of probability measures is a minimization of the KL divergence to the target pi. This objective function has the following structure. It's the sum of this potential energy and the entropy. The potential energy is V and the entropy is H. So we did a bunch of Wasserstein calculations of the Hessian last time, and we saw that actually the smoothness or strong convexity of this potential V on Euclidean space is equivalent to the same properties of this functional calligraphic V on Wasserstein space. We also saw that this entropy functional is convex, but non-smooth. And then finally, we discussed that like if you're strongly convex, the KL divergence on the space of probability measures, in general, this always implies that your functional satisfies a PL inequality. And in the context of sampling, this PL inequality is called a log-Sobolev inequality, and I rewrote what this log-Sobolev inequality looks like. It'll play a role today. So this log-Sobolev inequality says that the Fisher information to pi, which is just the expected norm squared of the gradient of the KL in Wasserstein space, and this is a expectation under mu of the norm squared of the grad log density ratio, and the LSI states that this upper bounds the KL divergence to pi. Okay, so what were we talking about last time, like the last 10 minutes? So in optimization, say we want to minimize some function f, then we know that in general, like you can always follow the gradient flow. But then in addition, if you're smooth, then you can actually do the explicit step, which I'll call the forward method. And the forward method, I just take my next iterate to be the previous iterate minus step size times the gradient. Okay, and then also we discussed the backward method, which does not require smoothness. And this backward method, what we do is we follow a gradient step. But the gradient is evaluated at the next point. And this is equivalent to minimizing a regularized problem, where we minimize the sum of our objective function plus 1 over 2h times the distance to the previous iterate. Okay, so these are kind of the three most basic building blocks of optimization. What I also mentioned is that when you have like a composite optimization problem, where we want to minimize f plus g, and then f is smooth, and g is non-smooth, then what makes sense in optimization is to consider the forward-backward algorithm. Where you just take a forward step on the smooth part and then a backward step on the non-smooth part, and then you get this iteration, xk plus 1. Okay, so some notation, this regularized problem is going to be called the prox operator for h times f. I know in Alessandro's talk, h was a function, but for me, h is the step size. So I take a prox step on the non-smooth term and an explicit step on the smooth term. Okay, and all of these things that I wrote down here for optimization have the property of being unbiased. And unbiased here just means that the optimization algorithm will converge to the minimizer that we're looking for if we iterate this, as long as the step size is chosen to be less than 1 over the smoothness. Okay, so this was the situation in optimization, and then I noted that in sampling, we also have a composite optimization problem. Under appropriate assumptions on V, this potential energy is both strongly convex and smooth, so it allows us to do an explicit step. And this entropy part is non-smooth. Okay, so let's try to like translate this picture into sampling a little bit more clearly. So it turns out I haven't really like justified exactly why this is the case, but the forward step for V would just be my next iterate, mu k plus 1, which is now a measure. It's just going to be the identity mapping minus h times the gradient mapping, push forward mu k. And at the level of particles, this says that I push forward my particle just by taking a gradient descent update. Okay, so this should be kind of intuitive, at least, like all the calculations that we did for this functional, the potential energy, exactly reflected the calculations we did in Euclidean space, and this is just another instance of that. I'm saying that the explicit step on V in Euclidean space, when you look at it on the space of measures, this is also the explicit step on the potential energy. And then for the entropy, what we were actually doing in Langevin is the flow. So the flow for the entropy, so remember that we said that the Langevin diffusion is the gradient flow of the KL divergence in Wasserstein space. So a special case of this fact, when you take the potential to be 0, then the Langevin diffusion just becomes Brownian motion. And then in the KL divergence, we're just ignoring the potential energy, so we just get the entropy term. So we know that Brownian motion is the gradient flow for entropy. And these are the two parts of the Langevin algorithm. We take a gradient step, which is a forward step on V, and then we run a Brownian motion, which is the exact gradient flow for the entropy. And what we know is that in general, this composition, the forward flow, so to speak, like we take a forward step on one part and then a flow on the other, this actually leads to a biased optimization algorithm. It doesn't converge to the minimizer. So this tells you like why, at least from an optimization perspective, why the Langevin algorithm, once you discretize in time, it gives you like a different stationary distribution from what we want. It's because like these optimization principles don't really line up. These are just the ingredients that we have to build an algorithm, and it just happens that we don't have really the ingredients to build an unbiased algorithm. However, it's still, I also mentioned that it's still kind of fortunate that we do have these ingredients, because like the part, I guess like out of these two parts, V and H, the part of the objective that I think of as more difficult is the entropy term. And it's for this more difficult term that we have access to the continuous time gradient flow, which is one of the two ingredients in optimization that actually does work for non-smooth optimization. So it is kind of nice that like the two ingredients that we have do kind of match what we can expect to be useful in optimization. So what I wanted to talk about today is try to like get past this situation and develop like unbiased algorithms for sampling. But today, I guess let's try to keep it a little bit more of an informal discussion. So feel free to chip in with anything that you want to comment on. And yeah. Okay, so today I want to discuss a little bit of my own research. So this is the topic for today is going to be this proximal sampler algorithm that I quite like. So this algorithm was I guess its applications were really fleshed out in this paper by Yin-Tat Lee, Rochi Shen, and Kevin Chan. And then a lot of what I'll talk about today is based on this paper of mine. I guess it's with collaborators Yongchen Chen, myself, Adil Salim, and Andre Bubasono. And in this paper, what we do is kind of give like a lot of the interpretations of this proximal sampler algorithm that I'll talk about today, and then also like the convergence proofs. Okay, so let's try to apply all these optimization techniques to like the context of sampling. So first of all, like one thing you can try to do is say like, I really like to run explicit methods because, or sorry. Like if I could implement them, I really want to implement implicit methods because implicit methods are much more stable. They don't require smoothness or anything. And you can always like prove like great convergence properties of them. So what does an implicit method look like if we just run it on the KL divergence? Well, what we want to do is take this like proximal operator and generalize it to the Wasserstein space. So this would be like a proximal method, I guess. Proximal algorithm for the KL. So our next iterate mu k plus 1 would be the minimizer over all probability measures of the sum of two terms the KL divergence plus 1/2 times the step size times the Wasserstein distance to mu k, the previous iterate. Maybe I'll use my previous convention of denoting this by the continuous time. Okay, so this scheme is known as the JKO scheme. Or also known as like the minimizing movement scheme. So this was originally like, I guess, like put forth in this paper by Jordan, Kinderler, and Otto that I mentioned last time. And that paper was the one which kind of identified the Langevin diffusion as the Wasserstein gradient flow. So how did they actually do this identification? It's not through all the calculus that I showed you. So the rigorous development of that calculus came later. What they did in that paper is that they actually considered this iteration scheme, which you can define without having any of the machinery of the calculus of optimal transport. To define this, all you need is the metric, right? So this makes sense in any metric space. And then they were able to show that as h goes to 0, this thing converges to the Langevin diffusion. So because this proximal algorithm should be interpreted as like a discretization of the gradient flow, whatever that gradient flow may be, and then they showed that this scheme converges to the law of the Langevin diffusion. Then they kind of concluded that the Langevin diffusion is the gradient flow. And then afterwards, like then we developed all this calculus to like make sense of this from a Riemannian perspective. Okay, so but what is the problem with this iteration scheme? And the problem is that it requires solving some minimization problem over all probability measures. Like how do you even like parameterize the class of all probability measures? It's an infinite dimensional space. It's just like basically impossible to actually implement this. Okay, so that approach kind of, we don't know how to make it work, but because of this interpretation of sampling as composite optimization, it tells us like maybe we shouldn't be looking at just the proximal algorithm for the KL. We should really be looking at forward backwards. So let's see what forward backwards looks like. Forward backward would be my next iterate looks like I take a proximal step for the entropy. And then I take a forward step on the smooth part of the objective, which I wrote out what the forward step is. It's identity minus grad v, push forward the previous iterate. Okay, and this proximal operator for the entropy it's the minimization over all probability measures nu of the sum of the entropy plus 1/2h times the Wasserstein distance. Okay, so this forward step we can implement because if we have a sample from UKH, we just push it forward by the gradient mapping, and then we'll have a sample from this push forward distribution. But given just that sample, we also cannot implement this proximal operator for the entropy for pretty much the same reason. But if you could implement this, then you can actually show that this forward backward method does converge very quickly to the target distribution pi. Okay, so somehow it seems like when we try to apply these ideas to Wasserstein space, we're stuck because all of these proximal operators are not really implementable. But what I want to tell you about today is a pretty non-obvious way of making some of these ideas work. Okay, so let's study this proximal operator of the KL divergence in a little bit more detail. Okay, so although like I said, to implement this proximal operator, you can't, in general, it's intractable. There is actually a case where you can figure out what this proximal operator is. And that's the case where I evaluate this proximal operator at a Dirac measure. So let's take mu to be the Dirac measure centered at y. And then I claim that this problem actually has an explicit solution. Okay, so what is the solution? If I write out the KL divergence, this is just going to be nu log nu plus integral of v d nu plus, now the Wasserstein distance to the Dirac of centered at y, there's only one possible coupling with the Dirac measure, so this is just y minus x, or yeah. Just the norm squared of the distance to y integrated under nu. Okay, but if I write it out in this way, then you can maybe see that this potential term and this, I guess there's also a constant coming from the KL divergence. Yeah, but you can see like these two terms, they really should combine because they're of the same type. Okay, so this is going to be v of x plus 1 over 2h times norm squared of y minus x d nu x plus a constant. Okay, so if we look at this expression, it looks like the same as the KL divergence, but what we've done is we've replaced the function v with v plus this quadratic term, like a regularized version of the potential. So what you can actually show is that this is the same thing as minimizing the KL divergence to a distribution, let's call it pi sub y plus a constant, where this distribution pi sub y has density proportional to e to the minus v minus also this quadratic part. Okay, are we all okay with this? So rewriting this proximal operator in this way, it makes it clear that the solution to this minimization problem is just pi y itself. So this distribution that I defined here is the prox for the KL starting at a Dirac. Okay, so at least when I start with the Dirac measure, then I have some explicit density for pi y. It looks like a regularized version of pi because I've added this quadratic part. And it looks very similar to what the proximal operator looks like in optimization. So that's also a good sign. And moreover, I claim that when the step size h is sufficiently small, then it's easy to implement this proximal operator. So why is that the case? Intuitively, when the step size h is very small, this quadratic term is dominating this expression. So if I have x above a quadratic, that's a Gaussian distribution. So for very small h, this whole distribution is extremely close to Gaussian. Yes.
Sorry, how do you know that this is exactly the, I mean, that this is precisely the proximal of, so that pi y solves the problem of the argmin over nu of that?
Just because like I rewrote the minimization problem as this,
Mhm.
and then the KL divergence is
Oh, it's zero. Okay.
it's
Sorry.
uniquely minimized.
No,
at
no,
pi
sorry, it was
yeah.
a silly thing. Okay.
Okay, so I claim that when the step size h is very small, it's possible to implement or like sample from this density. So the question is like, how small does h actually have to be? So the way that you can sample from this is via rejection sampling. Is everyone familiar with rejection sampling? No? Okay. But I'm not sure I want to explain like the details of rejection sampling because it's not the most interesting, I guess. But the basic idea is like if I want to sample from some density p, then what I need to do is I need to find some q, some other distribution q. Sorry, I really need to use a different color so you can see. So rejection sampling, I'll just like say the basic idea. You have some density p that you want to sample from, which is difficult, but you can evaluate what p is. You have some other distribution q, which you can sample from. This is called your proposal distribution. And then what you want to do is kind of scale up q so that it's always an upper bound for p. Something like this. Okay, so q tilde will always be an upper bound for p. And then what you do is you kind of draw samples from q, and then you either take your sample and from q and you either accept it or reject it. And the probability of acceptance is going to be like the ratio of the, like if I draw a sample here, like x from q, then the probability that you accept the sample is just going to be the ratio of how, like if I take the vertical line from x, how much of this lies under the curve p versus under the curve q tilde. So you can check that if you accept with this probability, then the sample that you get is actually going to be a sample from p. So that's kind of the procedure. You like draw a bunch of samples from your proposal, you accept or reject, and then you get samples from p. So this kind of sampling method is only really useful in 1D because like when you go to higher dimension, then the probability of accepting a sample is going to be exponentially small in the dimension, just because as the dimension grows, then like the volumes of everything scale exponentially in the dimension and so on. But here, we have the freedom to choose the step size h. So we can choose this step size very small so that this is very close to Gaussian. And then you might expect that if I propose samples from like a Gaussian distribution, then maybe I'll accept a reasonable number of times. And that is like the content of this. So this is kind of, I probably won't like discuss this in detail, but here's the implementation of this density. Suppose that this potential is smooth. And I choose the step size to be scaling as 1 over the smoothness times the dimension. Then So here's what you can show that with this choice of step size, and if you do the rejection sampling appropriately, then the algorithm will output an exact sample from pi y with the number of iterations that's just constant. And here I put in expectation because actually the number of iterations of this algorithm is random because you keep going until you accept the sample. But the number of iterations is going to be a geometric random variable because each try is going to be independent, and then there's some probability of success. You calculate that probability of success, and then you like make that probability of success constant with this step size. So we won't really discuss more the implementation of this, but now just know that with the appropriate choice of step size, we can sample from this density. Okay, but how does that actually help us with the problem of sampling from pi? So one observation we're going to make is that this distribution pi y can be interpreted as a conditional distribution. So the joint distribution associated with this is going to be a joint density on both x and y. And it's just x above minus v minus this quadratic. Okay, so I've kind of started with my distribution pi, which is a distribution on only x, but then I've augmented it to a joint distribution on two variables, x and y, like so. And then now let's just see what the two conditional distributions of this joint distribution are. So maybe for clarity, I'll write this as like superscript xy for the joint distribution. So what is the distribution of let's say y given x? Anyone? So this is an explicit distribution that you know the name of. What is this distribution? It's a Gaussian distribution centered at x. It's a Gaussian. The center is at x, and the variance is h. Right? Because to calculate this conditional distribution, I fix x, so this is just a constant. I get a quadratic, so this is a Gaussian. Okay, so this conditional distribution is very explicit. Now, what is the conditional distribution of x given y? Yep. So to calculate this conditional distribution, I consider y as fixed, and then I consider the density as a function of x proportional to this, but that's exactly the expression I wrote down here. So this other conditional distribution is the prox. Okay, so I have these two conditional distributions for this joint distribution. And so what I can do is I can apply Gibbs sampling. So this is the proximal sampler algorithm. And this is an instance of what's called Gibbs sampling more generally. Okay, so if I start off with an iterate xk, then I'm going to draw yk, let's say like yk, from the conditional distribution of y, given my value of xk, which is, as we saw, just a Gaussian distribution at xk. And then given the value of yk, I sample from the other conditional distribution, which is the conditional distribution of x given y, which is the prox. Okay, so I have this algorithm. Now, Gibbs sampling in general is always unbiased for the target. And the target is the joint distribution. So why is that the case? Like imagine that I start off with x drawn from the law of x under this joint distribution. Then this algorithm would then sample from the distribution of y given x according to the target. So y would then have the right distribution. And then I would sample from x given y. So then in the next iterate, x would have the right distribution. So clearly, like if you start off with a sample from the true distribution, it will remain invariant under this algorithm. So this algorithm is unbiased. And moreover, if you look at the distribution, the joint distribution of x and y, and I marginalize out y, then what do I get? So if I integrate over y, I will just get the integral of like this Gaussian factor. But the normalization constant of a Gaussian doesn't depend on where it's centered. So when I integrate over y, I will just get back e to the minus v. So under this joint distribution, the marginal law of x is the same thing as the original distribution e to the minus v that I wanted to sample from. So if I have this algorithm that samples from this joint distribution, in particular, by taking the x variable of the output of this algorithm, I will get a sample from e to the minus v. Are there any questions so far? Yes. Right. So all I'm saying is that if I take this joint distribution and then I marginalize over y, then I should get e to the minus v. So why is that the case? This is okay. So there's some like global constant of proportionality here, but then if I integrate, I get x of minus v minus 1 over 2h times it's a Gaussian on every side, and well, so when I integrate this part over y, the key point is that the normalization constant of the Gaussian does not depend on x. It will just be like 2 pi h to the d over 2 or whatever. So this is also just a constant. So the x marginal of this joint distribution is indeed like e to the minus v. Okay, so I have some unbiased algorithm actually for sampling from pi, which is really cool. I haven't told you yet how fast this algorithm converges, so we'll get there. But before we go further, let's like try to understand like the intuition behind this algorithm a little bit more. So you can kind of view this, like as you can see, this has like connections with the proximal algorithm from optimization. I want to tell you another point of view on this algorithm, which I find kind of enlightening. So we said that the Langevin algorithm is a forward flow. I run a forward step on the potential energy and then a gradient flow on the entropy. And that's Langevin. And we also said that these two components are mismatched and they lead to a biased algorithm. Okay, so if I want to fix this kind of mismatch between the two components of the algorithm, what can I do? So one way of fixing this mismatch is to use the optimization idea and do forward backward. So this is unbiased. But then we said we cannot implement this. Okay, but another way to try to fix this would be to keep the flow component, the Brownian motion, and try to figure out what should go here. Right? What would like fix this algorithm to make it unbiased for sampling from pi? So this flow part is actually just is the same as this, because when you run Brownian motion or equivalently you run the heat flow, it's the same thing as adding a Gaussian. And then now what I want to argue is that the second step of the algorithm, this prox evaluated a Dirac, is a way of kind of filling in this question mark here. Okay, so when you in optimization, the forward and backward algorithms, they're kind of loosely referred to as adjoints of each other. So there's this literature on like discretization of ODEs and stuff like that, where they do define what is the adjoint of an algorithm. Personally, I don't really understand the intuition behind their definition of adjoint. But what I'm going to show you is that what goes here is really an adjoint. An adjoint of the flow. Okay,
Sorry, a question just to see if I'm getting right the idea. Like, it's an adjoint with respect to which in the product.
Right, so the forward and backward algorithms being adjoint, this is it's not like super clear in what sense, but
Okay,
I'll tell you like exactly in what sense
Okay.
this prox is an adjoint to flow.
Okay, thank you.
Okay, so like we already saw an instance of using functional analysis to study diffusions when I introduced the generator of the Langevin diffusion. But more generally, like what you do is you encode the dynamics of your Markov process into like a semi-group of linear operators. And then you can use this like semi-group to study what happens. So like for the flow or Brownian motion, the semi-group is called the heat semi-group. And this heat semi-group, it maps functions to functions. So if I apply it to a function f and evaluate it at a point x, then by definition, this is just going to be, let's say the value of the Brownian motion, the expectation of f evaluated at the Brownian motion at time t, conditioned on the Brownian motion started at x. Okay, so this semi-group, essentially what it does is it tells you like how every single function or the expectation of it evolves along the Brownian motion. So it kind of completely captures the dynamics of the process. But what I haven't really specified to you yet is like on what space is this operator really defined? Like on what function, on what like class of functions is this acting on? And then we're really going to try to do an L2 theory because Hilbert spaces are the nicest ones. So let's try to think like what is like the natural space for this? Like what norm should I place on these guys? And also like thinking back to the context of this proximal sampler, let's just think about what's happening at stationarity for now. So at stationarity, I start off with x distributed according to, can I reach? Distributed according to the distribution of x, which is e to the minus v. That was bad. Okay, so in this expression, let's actually think of x as like coming from the distribution pi x. Okay, in that case, what I can do is like compute the norm squared of this with respect to the distribution of x, but then I can use Jensen's inequality for this, right? Okay, so, and then this is like by the like Tower rule for conditional expectation. I've like conditioned on the value of x, but then I'm integrating over this distribution of x. So this is just the expectation of f of bt squared, where this Brownian motion is started from the distribution pi x. Okay, so this is a like not the standard Brownian motion, which is started at 0, but started from a sample at pi x. Okay, so what is the law of BT? It's a Gaussian, but like started at pi x. So there's like various ways to describe what this law is. One way to describe this law is like I take this distribution pi x and then I evolve it by the heat semigroup. That's another way. That's one way of thinking about it. Another way to think about it is that this is actually just the distribution of y under the joint distribution. Why? Because if I look at the joint distribution and I marginalize out x, that's the same thing as like, well, like because like y conditioned on x is a Gaussian centered at x, and then if I marginalize over the distribution of x, I will just get like the output of Brownian motion, which was started at pi x. Okay, so where am I going with this? On the right-hand side of this inequality, I have f of bt squared. And this is just the L2 norm under the distribution of bt, which is pi y. And what is the left-hand side of this expression? This is a QTF. This function is QTF, and I took the L2 norm with respect to the distribution of pi x. Okay, so what I've shown is this inequality. So this actually tells me that QT is like a linear mapping between two L2 spaces, and it's a contraction. And the two L2 spaces that it maps between are L2 of pi y to L2 of pi x. Okay, because given a function f in L2 of pi y, this inequality tells me that QTF belongs to L2 of pi x. So it's kind of a different perspective on this heat semigroup, is that it's mapping between two different L2 spaces. But that's like the reason why we have two different L2 spaces is because pi x is not stationary for the heat semigroup. So when you evolve by the heat semigroup, you're ending up at a different L2 space. So these are the two spaces for which we're going to calculate the adjoint. Okay. So let's calculate what this adjoint is, qt star g, and let's evaluate it at y. Or should I say this? Actually, right. In order to define the adjoint, we really have to work with inner products. So this adjoint should have the property that if I, okay, so this thing maps from L2 pi x to L2 pi y. So this function is an element of L2 pi y. So if I take another function, if f belongs to L2 of pi y, the adjoint should have the property that if I take the inner product of f and qt star g in the inner product for pi y, this should be the same thing as qtf inner product with g in the inner product for pi x. And then this we can calculate because we know what qtf is. Okay, so let's use the language of the stochastic process again. So BT is the Brownian motion, but started at pi x. So this is QTF evaluated at B0, G at B0. Right, because B0 is distributed according to pi x. But this heat semigroup, QTF, it can be thought of as the conditional expectation of QTF at, it's the conditional expectation of F at BT conditioned on B0. Right? So then I can move this function of B0 inside. And so this whole thing is actually just the same thing as the expectation of f of bt, g of b0. But then I can kind of undo this calculation, but instead of conditioning on b0, I can condition on bt. So when I condition on bt, I will get f of bt times the conditional expectation of g of b0 given bt. Okay, just like playing around with conditional expectations. But why does this help? So bt is distributed according to pi y. So what I've shown is that this thing is the inner product between f and the conditional expectation of g of b0 given bt equals dot in the inner product of pi y. So now, like, if I just compare this expression with what I wanted to obtain for the adjoint, it tells me what qt star is. Qt star g at y is just a conditional expectation of g of b0 given bt equals y. Okay, so what does this calculation tell me? The semigroup QT, this is the forwards conditional expectation. What's the conditional expectation of the future given the past? And the adjoint of the heat semigroup is just the backwards conditional expectation. What's the conditional expectation of the past given the future? Okay, so that's a pretty nice interpretation of what this adjoint is doing. And now you see, like, this second step, the distribution of x given y. This is also just like the backwards conditional expectation along the Brownian motion. So this distribution of y given x, okay, it'll be clear if I write it like this. So xy in this like proximal sampler algorithm where x is started from pi x, this has the same law as b0 bh. Okay, because if you look at the joint distribution, then like the conditional distribution of y given x is just a Gaussian centered at x, but that's the same thing as a conditional distribution of Brownian motion on its like initial point, right? So these two distributions are the same. So in particular, if you look at the law of y given x, that's the same thing as the law of BH given B0, like Brownian motion forwards in time. And if I look at the other conditional expectation, conditional distribution of x given y, that's the conditional distribution of B0 given BH, which is the backwards conditional distribution. So these two like steps of the proximal sampler correspond to like the Brownian motion forwards in time and then backwards in time. Yeah, so like as a picture, I have okay, so I have the Brownian motion at time 0 and time h. But if I look at what this stochastic process does at the level of distributions, then this corresponds to the forward step of the proximal sampler, in which I sample Gaussian started at B0, and the backward step is this prox operator. And this might have been confusing, so maybe I'll pause for like questions about this interpretation.
I have a question.
Mm-hmm.
So, because you started with this calculation of prox of a delta, so but it's isolated, right? So it's not that when you run these prox point by point, this is the same as doing the prox of the measure, right?
Prox point by point. Sorry, what do you mean?
These prox that you wrote.
This one, yeah.
Yes, this is point by point. So it's not the prox of the measure of the law of YK.
Yeah.
Right. So
yeah,
this is not a
exactly.
sampler of a prox of the law of YK.
Exactly.
Right?
So this is nonlinear. So if I take the average of the prox operator with respect to some distribution nu for y, this is not the same thing as computing the prox starting from nu. Yeah.
The if you get a sample, then you average, and yeah, exactly.
Yeah. So what this algorithm is doing is the upper line, because like I have a sample from the law of y, and then I compute the prox starting from that, instead of computing a prox at the level of distributions. So this bottom line is not implementable. This top line is implementable through this sampler. And the key point is like in order to do this, we only need to calculate the prox at Dirac's.
Yeah, okay. Which is explicit, and you can do it fine because of the comparison. And so it's somehow it's you half linearized the problem.
Yes.
So you wanted to do the prox of HKL of nu. You don't do it. You don't linearize it totally in the way that you do maybe the forward flow or something like that, but you half linearize it in this way.
Yeah.
I don't know if it is okay.
Yeah, so
Thanks.
okay, this is the part where like, because we're heading into research territory, like some of these objects are not fully understood yet. So although we have like some very interesting interpretations of the proximal sampler, like maybe the way that I explained it to you just now, it still feels like at certain points we made like leaps of logic and just said, okay, we're going to do this, but like why exactly? So I think it's still very interesting to try to understand what's going on at like a deeper level. Yeah, so the amazing thing about this story so far is that despite the fact that we cannot evaluate the prox on general measures, we can only evaluate it on Dirac measures. Somehow this leads to some algorithm that you can run. But now comes the even more amazing part, which is that this algorithm, you can prove like amazing theoretical properties about this. Okay, so now comes the convergence analysis. So this paper here, like we give convergence under like a variety of assumptions. The one proof I'm going to focus on today is going to be the proof under the log Sobolev inequality. So we're going to assume that pi satisfies this log Sobolev inequality. And remember that this is like implied if the potential is strongly convex. Okay, before we do the calculation for the proximal sampler, let's just quickly review like the calculation for the Langevin diffusion, like why the LSI inequality implies fast convergence of the KL divergence for Langevin. Well, if pi t is the Langevin, then you can compute the time derivative of the KL divergence to the target distribution pi. Okay, so what is the time derivative of the KL divergence? Because like pi t is a Wasserstein gradient flow of the KL divergence, then the general like calculation rules for how to differentiate functionals along a gradient flow will just tell you this is equal to minus the Wasserstein gradient of the KL divergence. Okay, and this is what we said was the Fisher information. So if we write out what this Wasserstein gradient is, it's grad log pi t over pi in the pi t inner product. And the log Sobolev inequality precisely says that this is upper bounded by minus 2 alpha times the KL divergence. And then you use Gronwall to conclude the exponential rate of convergence of the KL. Okay, so the point is like we want to, in order to prove a KL convergence for the proximal sampler under a log Sobolev inequality, we're going to want to do some kind of differentiation of the KL divergence, like here. But we're going to need a few preliminary facts. Yeah, so let me just like state this preliminary fact that we'll need. Okay, so if pi x satisfies the log Sobolev inequality, then what happens to the log Sobolev inequality when I like convolve pi x with the Gaussian, or equivalently when I run the heat semi-group starting from pi x, then you can show that this is also satisfies the log Sobolev inequality with constant equal to this. Okay, so this is a little bit confusing because of like the inverses and so on, but wait, did I even do this right? Yeah, this should be right. But it's like maybe easier to think of as in terms of like the inverse of the log Sobolev constant. I'm not sure like what the best way to denote this, but in terms of the inverse of the log Sobolev constant, let's say that alpha log Sobolev inequality, we're just going to rename this as alpha inverse log Sobolev prime or something. Like so the log Sobolev prime is just the log Sobolev inequality, but I'm just like denoting the constant as like the inverse of this alpha. Okay, so what this says is that if pi x is alpha inverse log Sobolev prime, then pi x qt is alpha inverse plus t log Sobolev inverse prime. So like the inverse of the log Sobolev constant just adds, and this t is the log Sobolev constant prime of the Gaussian. So why is this the case? It's because if mu is the Gaussian, okay, so if mu is a Gaussian of variance t, then the potential for this corresponding to this Gaussian is norm of x squared over 2t. So this guy is actually t inverse strongly log-concave. So that means it satisfies log-Sobolev inequality with constant t inverse. So in terms of the inverse of the log-Sobolev constant, that's t. Okay, so that's the point, is that the log-Sobolev inequality, when you look at the inverse of the constant, it adds. So we'll need that fact. I think I'll probably skip the proof of this, unless you want to see it later. But using this, we're just going to calculate the KL divergence and see the convergence of the proximal sampler. Okay, so what is the picture here? So we have for the stationary distribution, pi x evolves by the forward step to pi y, and then the backward step takes you back from the law of y to the law of x. So this is what's happening at stationarity. In other words, like this pair pi x, pi y is kind of a fixed point of this process. Now what's going to happen is, for the algorithm, we're going to have some law mu k x. This is like the law of xk in our algorithm. And then we're going to run the forward process, which is just convolution with the Gaussian. And then you get the law of yk. And then we run the backwards process. And then we won't arrive at where we started. We'll now end up at mu k plus 1x. Okay, so this is what happens when you run the algorithm on mu k. So then the point is, like, if we keep iterating this process, we hope that we arrive at the fixed point, which is the stationary distribution, pi x and pi y. So in the forward step, what we're going to do is we're going to think of mu k y as, I started off at mu k x and I ran the heat semigroup for time h. That's the forward step, convolution with the Gaussian of variance h. So, and similarly, the distribution of y is pi x, but I run the heat semigroup for time h. So in order to see like how the proximal sampler is converging, what we're going to do is calculate the time derivative of the KL divergence of mu k x when you apply the heat semigroup and pi x when you apply the heat semigroup. Okay, so this if I can compute this tells me like I had some KL divergence here, and after I run the forward step of the algorithm, how does the KL divergence change? Does that make sense? So this is like a different calculation from Langevin, because Langevin we had like a fixed target distribution, and then we're just trying to calculate how the KL divergence to this fixed target evolves over time. But now, like for this algorithm, it's somehow more natural to think of the target distribution also evolving at the same time as the algorithm is evolving. So then we're going to track the two changes together. So this is calculation of the KL divergence along simultaneous heat flow. Okay. So let's forget about like the mu kx and pi x. To simplify the notation, let's just consider this the derivative of the KL divergence when both arguments are evolving along the heat semigroup. So what I claim is that this is exactly equal to minus 1/2 times the Fisher information between these two distributions. Okay, so this is, I don't know, I think it's pretty interesting. It tells you like before the Fisher information appeared as a time derivative of the KL divergence along the Langevin, where like we are only differentiating with respect to the first argument. Here, we're not differentiating along Langevin, we're differentiating along the heat semigroup, and both arguments are evolving. So it's kind of like a different calculation, but somehow the quantity that appears is still the Fisher information, and that's why like we can hope to apply the Log-Sobolev inequality here. So this might seem a little bit mysterious, but actually like to convince you that this is like not like a mystical coincidence, I'm going to do a more general calculation. So this is going to be our more general calculation. I'm going to consider the evolution of two measures, two different curves of measures, Buty and nu-T. Probably should put 1/2 here. I'm going to consider mu-T and nu-T, which are evolving like this. So this Laplacian term, this corresponds to Brownian motion. And then the second term corresponds to drift. So these equations are the evolution along this SDE. XT evolves according to BT plus Brownian motion. Okay, so basically like the same calculations that we did in the first lecture where we derived the Fokker-Planck equation for the Langevin diffusion. If you do that same argument for this SDE with drift, then you will get like these evolutions of measures. And I claim that for any processes like this, like if you take any SDE of this form where you have Brownian motion plus like some drift, and then you differentiate the KL divergence in time, where both arguments are evolving according to the same process, then you'll still get the Fisher information out. Okay, and in particular, like this generalizes both the Langevin calculation and the simultaneous heat flow calculation, because for the Langevin calculation, you just take this stochastic process to be the Langevin diffusion, and then you take nu-T to be the stationary process. So it's just always equal to the target distribution, and then this will give you like the Langevin calculation. But on the other hand, if you take the drift to be 0, then both of these are evolving just according to the heat flow, and then you get the simultaneous heat flow calculation. So the message of this is that when you do this calculation, the result doesn't depend on the drift. All right, so let's do this calculation. So at the end of the day, this is just a calculation, but it's kind of a surprising one, and then you do it, and then you see all the consolations. So we're differentiating in time the KL divergence, which is mu-T log mu-T over nu-T. So it's very easy to forget terms. So I'll just write this out like a little bit carefully. Okay, so we want to calculate this time derivative. So for this first term, the derivative of mu log mu, we said was log mu plus 1. So this first term, I'll have a log mu-T plus 1 times the time derivative of mu-T. And then the second term, I have to differentiate both with respect to mu-T and nu-T. So if I differentiate with respect to mu-T, I'll have the time derivative of mu t and then log nu t. And then if I differentiate with respect to nu t, I'll get 1 over nu t, or sorry, mu t over nu t times the time derivative of nu t. Okay, so now I'm going to plug in the equations for the evolution of mu t and nu t. Yeah, and I guess it might be convenient to rewrite these equations. So just as before, I want to write these equations as just a single divergence term. So if I write 1/2 times the Laplacian as a single divergence term, I'll get 1/2 grad log mu t. And then I'll have plus bt. And then similarly for nu t. Okay, so we're going to plug in this divergence expression for these time derivatives. Like this +1 is not going to matter because the time derivative of mu t integrates to 0. So this is the divergence of mu t 1/2 grad log mu t plus bt. Right? And then we have this term, which is minus log nu t times, well, yeah, I guess I could just combine both of these terms by writing here log of mu t over nu t. Okay, so this is the first two terms when I plug in partial t mu t. And then I have the third term, which is minus mu t over nu t times the derivative of nu t, which is a divergence of nu t 1/2 grad log nu t plus bt. Okay, and then now what we have to do is like integrate by parts to move all the divergences off. So when I integrate this guy, I will get a minus from the integration by parts, and then the gradient of log mu t over nu t. And then I will get the inner product of that with this vector field, 1/2 grad log mu t plus bt. And then all of this is integrated with respect to mu t. So that's what happens when I do the integration by parts for this first term. And then the second term, I get grad of mu t over nu t times the vector field for nu t. But don't lose hope, this calculation will go somewhere. So clearly, like if we want something to happen, we want to write this in terms of like a grad log mu t over nu t. So let's recall how that's done. Grad log of any function is just grad f over f. Okay, so grad f is equal to f times grad log f. So if I'll just copy down the first term again. Mu t. And then the second term, this thing is equal to grad log mu t over nu t times mu t over nu t. And here I had a nu t. So now you see, like when I replace this by a grad log, then this mu t over nu t, it's going to change the measure from nu t back to mu t. So now you can suddenly see that things are going to cancel. In particular, like this one's a minus sign, this one's a plus sign. this is the same as this. So these BTs cancel. That's why the final result doesn't depend on the drift term at all. And then I have a 1/2 grad log mu t, 1/2 grad log nu t, but this was a plus. They have opposite signs. So I have the grad log mu t over nu t, and then 1/2 of grad log mu t over nu t again, with respect to mu t, which is minus the expectation under mu t of grad log mu t over nu t, which is the definition of the Fisher information. So yeah, the calculation works. All right. So now we can just use this calculation plus the log Sobolev inequality. How does that work? Well, now what I'm doing is I'm differentiating the KL divergence. So I have the proximal sampler, which is going from X to Y in iteration K, which is the heat semigroup. And then the target distribution is also evolving according to the heat semigroup. By the calculation I did just up there, this is minus 1/2 of the Fisher information between these two measures. Okay. Now this is where I use the fact that pi x satisfied the log Sobolev inequality. So pi x convolved with, like you evolve it by the heat semigroup, is also satisfying a log Sobolev inequality. So then I plug in what is the log Sobolev constant that lemma gives me. Right. Because like that will lower bound the Fisher information by 2 times the log Sobolev constant. So give me 2 over alpha inverse plus t times the KL divergence. Okay. And then this I can just write as minus alpha over 1 plus alpha t. Okay, so the point is, like, I have a log Sobolev inequality for all of these distributions, so I can lower bound the Fisher information by the KL. There's one difference with the Langevin calculation, which is that the log Sobolev constant now depends on t, a time-dependent constant, but we can still use Gronwall. And what will Gronwall tell us now? So Gronwall will tell us if I integrate this between time 0 and h. So what is this at time h? That's just going to be, like, at time h, I've moved completely from x to y. So this is just mu ky and pi y. This is bounded by this expression at time 0, which is just the KL between the x's. Times, and then this is what Gronwall gives you, the exponential of the minus integral from 0 to h of these constants. Okay, so this is just the generalization of Gronwall to time dependent constants. Okay, so now we need to do a little bit of calculus to figure out what that integral is. I don't need this anymore. Okay, so this should give you, this is like a 1 over t kind of thing, so this should give you a log log of 1 plus alpha t plus alpha h, right? Yeah, so that's what the integral is. Therefore, like if I have exponential of minus this quantity, then this is just 1 over 1 plus alpha h. Okay, so what have I shown to you? I've shown to you that in one iteration of the proximal sampler, when I go from x to y, the KL divergence of mu k y to pi y is bounded by 1 over 1 plus alpha h times the KL divergence between mu k x and pi x. Okay, so in this forward step of the proximal sampler, I get a contraction in the KL divergence with something that depends on the log Sobolev constant. So this tells me from x to y, but I need to go back. So I need to understand how does the KL divergence between the x's at the next iteration compare with the KL divergence between the y's. Okay. So let me tell you like the short answer and then the slightly longer answer. So the short answer is like this is definitely true just because of what's known as the data processing inequality of the KL divergence. So the data processing inequality says that if I apply the same like Markov process to both arguments, then the KL divergence can only decrease. So then you get this inequality. And since I already got the contraction that I wanted in this first step, this is already good enough to prove convergence. Okay, but what is the slightly longer story? The slightly longer story is that you can actually put a symmetric factor of 1 over 1 plus alpha h here. So what is the idea behind this thing? Well, just in this forward step, essentially what we did was we differentiated along the forward Brownian motion. In this backward step, you differentiate along the backwards Brownian motion. So there's a fact that the time reversal of a stochastic differential equation is again a stochastic differential equation. You can write down what this reverse SDE looks like. Then you can repeat the Fisher information calculation that we did here. And yeah, spoiler, like it works out for the backward direction as well. And then you can get this contraction in the backward step too. So putting it together, if I look at iteration k to k plus 1 just in the x coordinate, then I get a factor of a square here. Okay. Right, so a couple of comments. This factor of 1 over 1 plus alpha h squared, this is completely sharp because it matches what you get for the convergence rate of the Euclidean proximal point algorithm. So this is actually like exactly what you expect. And the thing is, like, we achieved this convergence rate without being able to implement the proximal operator on Wasserstein space. That's where we started this whole story today. Is we cannot compute the proximal operator. Let's at least try to compute it for Dirac measures. But the really amazing thing is that this is already enough to get you like the convergence rate of like a proximal algorithm on Wasserstein space. Okay, so that's one amazing thing. Another thing to notice is that, right, so I told you that this, like the backward step, the proximal operator at a Dirac, you can implement it exactly via rejection sampling with the appropriate step size. If you implement that exactly, this is like the outer loop of the proximal sampler. It converges exponentially fast to pi with no bias. So unlike the Langevin algorithm, when you like do this algorithm with the step size h is 1 over beta d, which is what we said we wanted for rejection sampling, then what is the complexity bound that you get for the proximal sampler? Well, you work this out, and then you'll see that the number of iterations of the proximal sampler to get the square root of the KL divergence at iteration n to be at most epsilon is O of beta over alpha d log of the initial KL. Okay, so this is the complexity bound that you get for the proximal sampler. And let me just compare with the Langevin result that I wrote down yesterday. So the comparison with Langevin got O of beta squared d over alpha squared epsilon squared log KL over epsilon squared. Okay, so the things you should notice are that here the dependence on the accuracy for the proximal sampler is log 1 over epsilon. That's because we converge exponentially fast to the target. Whereas in the Langevin, we had this 1 over epsilon squared dependency because of the bias. So that fixes the bias problem. The other thing is like, in terms of the dependence on the condition number, beta over alpha, we also improved here. So that's because the coupling analysis of Langevin that I gave you last time wasn't really tight, I guess. It's like kind of tricky to do the discretization analysis of Langevin in a way that you get all like the tight constants. But this algorithm was like the analysis of it was so like clean, I guess, that we didn't lose anything. We didn't, yeah. So then you get the correct like beta over alpha dependence. And then I just mentioned rejection sampling as one possible way of implementing this this sampler, the proximal operator. But what this algorithm really tells you is that in order to solve our original sampling problem, it just suffices to implement this prox operator. So it kind of reduces the problem of sampling from a general distribution to the problem of sampling from this prox distribution, which is very nice. It's like strongly log-concave, log smooth, with the appropriate choice of step size. It's like very close to Gaussian. And then like there's some recent work, not really out yet, which shows you can implement this even faster. So you immediately get improvements in all these convergence rates. Okay, so let's see how much time we have left. And oh, okay, I need to end.
Okay, so thank you very much. I guess we are a bit over time, but it's fine. It's the last. So do you have questions, comments, curiosity? Yes, Andrea?
Usually alpha and beta are small, or the comparable, or they whatever we want to try to kill a bit the big O.
Beta over alpha is the condition number of the problem. So it just depends on whether your problem is
Okay.
very ill conditioned or not.
Okay.
There are some problems for which the condition number matters a lot.
Okay. Thank you.
I have a question, which is so it seemed to me that so in your proximal sampler, you basically take your base distribution, you multiply by something which is dependent on epsilon, and then you do this alternate projection, right? In some sense. So instead of putting a normal, could you put something else?
Yeah, so more generally, like the idea is like you run a stochastic process forwards in time and then backwards in time, and then you iterate this. And then like this idea has also been used in like deep learning for like DALL-E 2, if you've ever heard of it, for generating images. Is also based on the idea of running a diffusion forwards in time and backwards in time. I think it's interesting to consider how the choice of the forward process, you want it to like adapt to the geometry of your problem somehow if you want the best possible results.
What I was thinking it was okay, instead of doing the heat flow, you do the Holstein-Uhlenberg process. So
Right.
basically you want to, if you are in a case where, I don't know, your function is strictly log-concave, then maybe you want to do Holstein-Uhlenberg because you want to reach faster so in that case, but you get the same rates, I guess.
Right. So for Ornstein-Uhlenbeck is actually what they do in diffusion models. So that is essentially like a time reparameterization of this. Like, turns out the more important distinction is whether I choose the step size h to be small or large. So the analysis I've been doing is when h is small, which allows you to implement this prox operator exactly. But then because h is small, you suffer from the same problems as Langevin, as in like the outer loop will get stuck in deep wells. Whereas like if you take h very large, the outer loop is going to converge in one step, but then the implementation of the prox operator, then you can try to devise other strategies for this, such as discretizing the reverse SDE. And that is what diffusion models do, is discretize this reverse SDE. Yeah.
Thank you very much. So if you don't have other questions, comments, okay, we thank again Sinho. And I guess it's time to thank everybody. So thank, of course, all the participants and all the speakers of both the workshop and the school. It has been fantastic for us organizers. And thank also, of course, to the other organizers, so Augusto, Silvia, and Lorenzo. And thanks to Scuola Normale and Centro De Giorgi hosting and giving us lots of, they were very kind and very efficient. So let's thank everybody that I said again.